Okay, so this is part 2 of our divergence theorem proof for a rectangular box. In the first part of the video, we showed that the flux of our vector field F through the faces of the rectangular box was given by these three double integrals. So in order to verify the divergence theorem holds for a rectangular box, we're going to have to show that this volume integral of the divergence over our rectangular box equals our surface integral. Okay, so I need to show this. Alright, so let's work on this triple integral now. So let me erase a few things and we'll keep going. Okay, so for ease of notation, I'm going to write R to denote our box. And recall how our box was defined. We had our point x0, y0, z0 here. We then have our rectangular box. And from here to here is delta x. From here to here is delta y. From here to here is delta z. Okay, so, and recall also the divergence by definition. So here's my vector field up here. So it's going to be the f1 component function derivative with respect to x, partial derivative with respect to x, f2 function partial derivative with respect to y, f3 function partial derivative with respect to z. So that's my divergence definition. And I'm doing the triple integral over our rectangular box here. So x is going to go from x0 to x0 plus delta x. Y is going to go from y0 to y0 plus delta y, and z is going to go from z0 to z0 plus delta z. So that's going to be my limits on my triple integral here. And since we're integrating over a box, I can change the order of the integration around, so I can put y first and then x if I wanted to. Let's just keep it like that for now. So let me put the limits here. So it's going to be x0 to x0 plus delta x, y0 to y0 plus delta y, and z0 plus z0 to z0 to z0 plus delta z. So let me erase this box now and I'm going to write it down here. Okay. Okay, so I put the limits on here. I still have the box here. So again, the first one, it should be x0 here. x0 plus delta x, because the x is going from x0 to x0 plus delta x, the y is going from y0 to y0 plus delta y, and the z is going from z0 to z0 plus delta z. Okay, so now I'm going to break this into three separate triple integrals and change the order of integration. I'll explain why in a second here. So let me do it here. Okay, so I'm going to break into three triple integrals and change the order of integration. So I'm going to take my triple integral. Since it's linear integrals, you can multiply it into each of these. So multiplying into the first one, that's how I got this one. I didn't change any order of integration here. Still the same dx, dy, dz. And the thing is, I want to get this variable here lining up with the variable down here, so they're lined up here. But then I'm going to multiply this triple integral into the second one, the f2 guy, which I've done here. But I did change the order of integration because I want the y to correspond with the y here. So I changed the x and y around, which I've done here. And again, I can do that because I'm integrating over a box. So, but in general, you can't just change the order of integration around that easily. Okay, and the last one, multiplying it in here with the f3 guy. And then I want to change the order of integration so the z comes first, which I've done here. Okay, so now I'm going to apply the fundamental theorem of calculus to each of these guys here. So let's recall the fundamental theorem of calculus. Okay, so recall the FTC, or the fundamental theorem of calculus, says the integral from a to b of, say, f prime with respect to t, what's going to be the antiderivative of f prime, which is f, evaluated at a, subtract f evaluated f evaluated at b minus f evaluated at a. So that's our fundamental theorem of calculus. I'm going to apply that to this one, because notice here you have a derivative with respect to x and you're integrating with respect to x. So you could apply the fundamental theorem of calculus to this guy. And here you have a derivative with respect to y and you're integrating with respect to y. You could apply the FTC to this guy also. And here you have a derivative with respect to z and integrating with respect to z. You could apply the FTC to this guy also. So let me just circle these guys. Okay, so again, I'm going to apply the FTC to these circle parts. Again, because I'm taking derivative with respect to x and integrating with respect to x, derivative with respect to y, integrating with respect to y, derivative with respect to z, integrating with respect to z. Okay, so let's do that. So let me erase a few things and we'll start applying our FTC. Okay. Okay, so I've rewritten it over here. So here's our three triple integrals. So we're going to apply the fundamental theorem of calculus to this guy first. So again, it's going to be the integral of f prime, so it's going to be f of b minus f of a in general. So here the a is x0, the b is x0 plus delta x, and this will be f1 then. So let me write the answer here. So applying the FTC to this first guy here, it's going to be f1. The b value here would be x0 plus delta x. So you're going to be evaluating the f1 at that x value. And then the y and z are, just use y and z here. Then minus f1 of your a, which is x0, then y and z here also. And it'll be still derivative with respect to yz. So that's this one taken care of. Let's apply the FTC now to this guy here. So let me write the answer here. Okay, so applying the FTC to this guy, there's going to be f2 evaluated at our at our b value, which is going to be the upper one here, limit. So y0 plus delta y, which I've done here. And for the x and z, just put x and z. Then subtract, putting in y0 in place of y and xz here. So it'll be this guy here. And lastly, let's apply the FTC to this one here. So let me write the answer over here. Okay, so applying the FTC to this last guy, it's going to be f3 of xy, then put in place of z, put in z0 plus delta z, minus f3 xy, and in place of z, put in z0. So we get these three triple integrals. And if you compare this to what we got from doing the surface integral of f over our faces, you can see, I'll let you verify, it's the same. So we've shown then, okay, so we've shown this. We're showing that up here, our volume integral of the divergence over a rectangular box equals the surface integral of f over our faces, the faces of the rectangular box. So this then verifies the divergence theorem for the rectangular box. So let me just summarize what we've shown here now. Let me erase a few things and we'll summarize what we've shown. Okay, so to summarize, we've proven now, let's call it theorem 16. So we've shown that the flux of your vector field f through S equals the volume integral of the divergence of f over the rectangular region. When your f is your vector field here, I guess we're assuming the component functions have continuous partial derivatives, and S is the faces of the rectangular box with normal vector directed out of the box. So it's pretty much, we've proven the divergence theorem for any rectangular box. Okay, so in the next video we're going to show how we can take this and use it to prove the more general divergence theorem. And in the next video we'll also prove some properties about the divergence theorem. Okay, so let's leave it there in this video. Okay.